All right, here we are again. So now today, the first thing we're going to do is work on the chapter 5 problem set number 1. And then when that's done, we'll get back to the chapter 5 material when we were just about ready to start scientific notation. All right, so let's take a look at these. And let me get this thing open. And here we go. So now you can see this is a fairly short one. The second and the third ones are fairly long. So my plan here is to cover one of these each day for the next 3 times that we meet. So we'll do this one today. We'll do number 2 on Thursday and number 3 the next Monday, assuming that we finish the material. And so this one won't take that long, but the second and the third ones are fairly long. So we'll see how that goes. We may have to play this by ear just a little bit. But so I'm going to write up all the answers here as usual, and I'll be posting them when we're done in case you missed something. And you'll be able to see how you did. And hopefully you had time to work on these, because that's the only way to really find out if you understand them or not. Okay, so let's do it. Let me get back here. Checking out to see who's here. It looks like most of you have arrived, so we can get started. All right, so let's start at the beginning with the factors. Now, the factors are pretty straightforward, but the problem with factors is that it's easy to overlook some of them. All right, so for example, let's start with 16. Now, the best way to do this, I think, is to start typing out or writing out the ones that you recognize. For example, here, we always will have 1 in the number itself. This one happens to be an even number, so we'll have 2 times 8. 3 doesn't look promising, does it? But 4 times 4 works. And now, once we get to this point, we actually can stop right there, because even if we found another one, for example, if I kept looking through all the natural numbers for the next factor, the next one would be 8. And there's no point in writing 8 times 2, because I've already got 2 times 8. So that means we can stop right here, and we conclude that our factors are 1, 2, 4, 8, and 16 are the only factors of 16. All right, so that was easy, good. Now, how about 225? Now, that one's a little bit more challenging. So let's start with 1, of course. 1 times 225. Now, clearly, this is not an even number. It will not be divisible by 2. How about 3, though? Turns out there's an interesting little rule about 3. If you've forgotten it, maybe you learned it, maybe you forgot, I'll put it in parentheses here. If the sum of a number's digits are a multiple of 3, then the number is divisible by 3. Okay, so here, the sum of the digits is 2 plus 2 plus 5, which is 9, which is a multiple of 3. This guarantees that 225 is divisible by 3. Well, that's a handy little rule, don't you think? Oh, yes, it is. So we're going to have, what in this case, it happens to be 3 times 75. I like that rule because it's so easy. Now, of course, you know some of the others. There's a couple you probably are aware of. For example, if any number ends with 0 or 5, it can be divisible by 5. And if any number ends with 0, we know that it can be divisible by 10. Now, the book actually has a list of rules for all of the digits. It turns out there's a rule for every single one of them. But some of them are just so complicated that it may not be worth your while to try to remember them. But the 3 is easy. I like that one. 3 is easy, 5 is easy, 2 is easy, because that just means it's an even number. But when you get to numbers like 7 or 8, it starts to become a lot messier. So what you do instead is you just try it. If you're not sure, for example, if a number divides evenly into 225, just take out your calculator and you'll find out pretty quickly if it does or it doesn't. Now, 4 clearly is not a good choice. How about 5? Yes, the number ends with a 5, therefore it must be divisible by 5. And what number does that give us? 45. How about 6? No, it doesn't look good. 7, I don't think so. 8, no. Oh, wait a minute. How about 9? It turns out this number is equal to 9 times 25. And then guess what? It turns out that 225 is a perfect square. It's equal to 15 times 15. So that should do it. Man, that's a lot of factors. There they are. That's the whole list. We didn't miss any. All right, very good. Oh, the word is correcting my grammar here because the subject of that sentence is some. That should be is. Whoops. Okay. All right, there we go. Find the factors of 126. Okay, very good. 1 times 126, even. It's an even number. How about 3? Do those digits add up to a multiple of 9? A 3 rather? They do. Okay, so therefore 3 goes into this very nicely. It's 42. How about 4? No, that doesn't look good. 5, no, absolutely not. 6, wait a minute. 6 times 21. 7. Now you'll be shocked to discover that this number is divisible by 7. That's right. 7 times 18 is in fact 126. How about 8? Oh, no, no 8. But how about 9? What about 14? Yes. Now, of course, we can rule out 10, 11, 12, 13. And since we already have a 14 here, we can stop right there. So we just gather them up. 1, 2, 3, 6, 7, 9, 14, 18, 21, 42, 63, 126. Interesting. That's a lot of factors. Wow. And here's 54. All right, let's try that. 154, 227, 3. You notice the digits add up to 9, so we're guaranteed that it's divisible by 3. 18. 4, no. 5, no. 6 times 9. I guess that's it. So that's that. Man. It's amazing how many factors some of these numbers really have. Okay, so let's look at some multiples now. Now, multiples are easy. All you're doing is multiplying the number by the first 5 natural numbers. So are 3, 6, 9, 12, 15. End of story, you're done. Multiples of 7. 7, 14, 21, 28, 35. Now, 10 is as easy as it gets. Yeah, you can do that one in your head. And then we have for 12, 12, 24, 36, 48, 60. All right, and then finally we'll do 15. 15, 30, 45, 60, and 75. All right, well, that was nice and easy. If only all the problems were so simple. So what we're building up to now is prime factors. Now, we've already seen that there's a nice, easy way of getting to these prime factors by drawing what's called a binary tree. And of course, bi means 2, which means each node on this tree has 2 branches. All right, so are we ready? I don't want to rush anyone. Okay, let's carry on. So how about 16? Let's try that one. Now, of course, everybody loves to draw pictures. This is no exception. Let's try 2 times 8. And I just would point out, if you tried 4 times 4, you'll still eventually get the same answer. And once you get to the point where you only have prime numbers, you're done. And if you want to write this, you can write it as 2 to the 4th if you want to, but the bottom line here is that 2 times itself 4 times is 16, and these are all prime numbers. So this expression here is sometimes called the prime factorization of 16. Oh, but the question only asks for the prime factor. So all you need is the 2's. Just write them all out, or else write it like this. All right. Now, how about 18? So we'll have 2 times 9. And oh, that's it. We're done. So 18 equals 2 times 3 times 3. This is the prime factorization of 18. 2 times 3 times 3. Nice. 1296. Oh, this is going to take a while. Oh, man. All right, let's do it. So since it's even, you may as well cut it in half. Man, that's a lot of even numbers. Oh, here we go. We got one that's not even. Now, 81, of course, is 9 times 9. Each one of these is 3 times 3. So that's a lot of prime numbers. I've got 1, 2, 3, 4 2's and 4 3's. Man, that's a lot. And of course, you know, you might be tempted to write it as 2 to the 4th times 3 to the 4th, because it means the same thing. This is the prime factorization of 1296. Okay, now, how about, oh man, 1960, that's probably going to be a real whopper. 1960. Two, 980. 2, 490. This is even as well. 2, 245. Now this one is divisible by 3. Okay, so it should be 245 divided by, wait a minute, no it's not. My fault. It's divisible by 5 though. Okay, this is 5 times 49. And then, oh, look at this, 7. 49, of course, is a perfect square. 7 times 7. And so when we're done, we're going to have 1960. And we have 1, 2, 3 2's. It's 5 times 7 times 7. All right, or once again, you can write it as 2 cubed times 5 times 7 squared. Nice. All right, I think there's one more here. Ooh, 17. Oh my God. Now, you can take it and write it out like this. Remember, this is not prime. So that means there's only one prime factor of 17. So 17 is the only prime factor of 17. And that's it, you're done. It's unusual, but that's how it works. All right, now with these greatest common factors, you might recall that in these cases, one way we can obtain them is to get to the prime factorization of each number and see what they have in common. So 3 is a prime number. So 3 is the only prime factor of 3. Whereas with 9, we have 3 and 3. So the prime factors of 9 are 3 and 3. So they only have one in common, which is the 3, which means that the greatest common factor of 3 and 9 is 3. All right, here we go. 10 and 35. Let's see what happens there. Well, those were easy. So 10 equals 2 times 5. 35 equals 5 times 7. Okay, they only have one prime in common, which is 5. So the greatest common factor of 10 and 35 is therefore 5. Very good. Now, then we're going to have a very oddball case coming up. And that's the thing in math, you're chugging along with all these wonderful rules, and all of a sudden an exception jumps out. We have to be prepared for these very strange cases. How about this one? 7 and 10. All right, so here's the strange part now, because 7 is prime, therefore the only prime factor of 7 is 7. The prime factors of 10 are 2 and 5. 10 and 5, 10 and 7 rather, have no prime factors in common. So what is their greatest common factor? In a case like this, the greatest common factor is defined to be equal to 1. Okay, so if you have two numbers without a common prime factor, then we say that their greatest common factor is 1. Even though it's not prime, it's still considered to be a factor of both numbers. Do you find that very disturbing? Yeah, what's going on here? What happened? And here's an interesting side note. This is just for your benefit. When this happens, this is notation or terminology. This happens, the two numbers are said to be relatively prime. They're not necessarily primes, but compared to each other, they're prime. So you don't have to memorize that, but I just thought I'd throw that out there because it's kind of interesting. Relatively prime. So, okay. Now, what about this case, 6 and 11? Oh, no, I think we have another problem in our hands. Because look at them. 6 has prime factors of 2 and 3, but look at 11. Oh no. So once again, we run into the same issue. The prime factors of 6 are 2 and 3. The only prime factor of 11 is 11. 6 and 11 have no common prime factors. Therefore, we say that the greatest common factor of 6 and 11 is 1, and 6 and 11 are, again, relatively prime. All right. Now, least common multiples, I think everyone can agree, least common multiples are pretty straightforward. They can be time consuming, but it's not hard to do conceptually, because really all you have to do is write out a list of each number's common, their multiples. And when you find the smallest one that they have in common, you're done. Like here, I can already stop. Why? Look what I discovered. Oh yeah, look at that. So therefore, we conclude that the least common multiple of 5 and 10 is 10. And so I'll make a note here in parentheses. Sometimes the least common multiple of two numbers is one of the numbers. That can happen. Don't be shocked when that happens. All right, how about this one? The multiples of 12 are 12, 24, 36, 48, 60, 72, ... And then the multiples of 24 would be 24. Oh, look at that. I can already stop. Why? Look what I found. Well, guess what? We found it. The least common multiple of 12 and 24 is 24. And once again, you see that principle. Sometimes it is simply one of the two numbers. And that happened again here. All right. Nobody shocked, are they? Good. We don't want any shocks in our class. All right. See, that's the beauty of math. There's no shocks. All right. Everything is exactly what you'd expect. There's no surprises. Is that one of the nice things? Is that one of your favorite features about math? No shocks? Good. Everything, whatever it is, it is. There's no mysteries involved. Everything is what it seems to be. Ooh, I like that. In math, everything is what it appears to be. Ooh, I like that. Not only that, but here's one of my favorite. I made this up, by the way, and you can quote me if you want. Watch this. There is no such thing as maybe in math. Ooh, is that pretty deep? Because the answer is either yes or no. There is no maybe. It's yes or no. That's all we have to choose from. In other disciplines, you do have maybes. Like, which painting do you like the best? Well, on the one hand, on the other hand, blah, 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 blah. There's no absolute anything in art. But in math, it's just the opposite. Or music, for that matter. All right, anyway. So the way this works, we don't need this anymore. The least common multiple here, same thing, multiple of 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And then multiple 7, 14, 21, 28, 35, 40. Oh, wait a minute. I went too far. And I also got a mistake in here too while I was at it. There we go. All right. So you can see there is a 35 that they have in common. And therefore we're done. And this brings up another interesting point. 35 is the least common multiple of 5 and 7. And I'll just make a note in parentheses here. Sometimes the least common multiple of two numbers is the product of those two numbers. Okay, so that one is always a potential candidate for the least common multiple, just the product of those two. That one's always potentially on the table at least. All right, I think, is there one more? Yes, 6 and 10. Now this one's easy. Anytime we get tens involved, it makes things so much easier. I think it's pretty clear where this one is going. All right, here we go. It's easy. 30. Okay, so the least common multiple of 6 and 10 is 30. And you notice it's neither the product of the two, nor is it one of the two individual ones. It can be anything. All right. Now for the next section, I will find it necessary to do a poll. Here we go. This is more of an opinion survey. Okay, so here we go. Okay. Here we go. We haven't had a good poll in a while. Oops. No, that's not what I wanted. Oh no, what's going on here? We're having chaos. Well, I am shocked to see this. Shocked, I tell you. No, I am not, because over the years, it's been made very clear to me that people don't particularly care for word problems. But you know what? In a way, they're just like any other problem. What tends to happen, though, is that it's easy to not understand what exactly you're being asked to do. I don't even want to know what none of the above includes. I just left that open. I'll assume that you just mean you're indifferent to them. How about that? So anyway, but let's take a look at the first one. Now, this first case tells us we have two people on a circular bike trail. And when we're allowed to walk on the campus again, you'll see that it does in fact have a big circular trail that you could use. The campus is enormous. Have you ever noticed? I mean, if you ever really walked around, it is huge. There's an entire football field hiding over in the corner somewhere where nobody even notices it. It's over there somewhere. But if you were to get on a bike and ride around, you'd see that you're just making a big circle. So just imagine the following scenario. You and your friend get together, say, you know what, let's do this. Let's start here, right in front of our room, and we'll go around the circle clockwise. And when we meet up again, we'll go to lunch. The only problem is the first person can get through this around the circle in 24 minutes. The second person takes 36 minutes. So will they ever see each other again? Well, eventually they'll have to catch up with each other. The question is when. That's what we want to know. How long will it take before we're both at the same point, and then we can go get lunch? Well, why don't we try this? When will person one, we'll call them person 1 and 2, reach the starting point again? Well, in 24 minutes, 48 minutes, 72 minutes, 96 minutes. Every 24 minutes, they'll be back at the starting point, assuming that they don't get tired or drop out or something. When will person 2 reach the starting point again? 36 minutes, 72. Oh, wait a minute. What's going on here? I see that there's a point when they'll both be there in 72 minutes. That's right, 72. And so you recognize this now. This problem is just a least common multiple problem. Now, if you recognize that, look how easy it turned out to be. 72, is the least common multiple of 24 and 36. Therefore, in 72 minutes, they'll both be back at the starting point. And they'll be plenty hungry, so they can go off to lunch then. After 72 minutes of bicycling, they're going to be starving. So the timing is perfect. Okay. All right. So that's that one. Now there's another one. This involves lighthouses. Lighthouses are cool. They're designed to make sure ships don't crash into the shore. You probably heard about it. There's a pirate ship that actually crashed off the coast of Cape Cod in the early 18th century, the Whydah. And it was recently dragged. I mean, the searchers actually found it, and they were able to recover a lot of what was on board, and that includes a pretty significant amount of silver. And so yeah, they're saying how it's one of the few pirate ships where the treasure was actually recovered. And so they're out there still looking. There's a museum in Cape Cod where they have all the items that they brought up from the ship. So you can see what a pirate ship actually looked like. That's right. So if you are familiar with Cape Cod, does anyone here ever visit it? Yes, it's the best ever. In Hyannis, they have a museum. It's called the Whydah Museum because that's the name of the ship. And if you want to see all this, now the treasure is not in the museum. No, there's too much. They don't have that kind of security there, but they do have like all the other equipment and all the items that the pirates were using. And wow, it took a long time, but they found it. And with all that treasure on board, I'm sure that paid for the whole thing. So it happens. But the point now, Cape Cod is known for having a very rocky shore. The ocean is very treacherous there. So even with the lighthouses, it's not that uncommon for ships to crash. And so, well, especially pirate ships that are trying to avoid the British Navy whenever possible, they're going to take chances that other ships might not take. So they got a little too close there. And before you know it, oh boy, we're at the bottom of the ocean. So these lighthouses now, there's 4 of them. The first one flashes every 10 seconds. So when will lighthouse 1 flash again? 10, 20, see, it's every 10 seconds. How about lighthouse 2? Now, lighthouse 2 is going off every 15 seconds. You can see where this is going, I think. When will lighthouse 3 flash again? That's every 20 seconds. Look how easy this is. Whoops. And then when will lighthouse 4 flash? They're going off every 30 seconds. 30, 60, 90, 120. And you can see what do they all have in common? Oh my God. every 60 seconds, they'll all flash at the same time. So in other words, because this is the least common multiple, 60 is the least common multiple of 10, 15, 20, and 30. And maybe you didn't know, but you can have a least common multiple and a greatest common factor for that matter for more than two numbers at a time. So between the four of them, their least common multiple is 60, and now you know how often they'll all flash at the same time. And in fact, if you're lost at sea and you don't know what time it is, you might be able to figure out what time it is by watching those flashes. Anyway, well, that was that. So we're done with our problem set. I think we survived unscathed. Good. All right, so I'm going to post this when we're done. And tomorrow, for Thursday, I want you to have number 2 ready, and we'll do the same thing. And then number 3, we'll try to have it ready on next Monday. In the meantime, we're ready to go back to our slides. Chapter 5C, now we were ready to start discussing scientific notation. And you might recall, scientific notation is just another way of expressing numbers that are either huge or tiny. And what kind of classes in high school were you most likely to use them? Not English, unless you were reading novels about math, which is not impossible. Science, chemistry, physics, the hard sciences, where you sometimes encounter gigantic numbers like the speed of light and tiny numbers like the weight of an electron. They're so large or small that writing out all the zeros is very awkward. So instead, we came up with this approach, which makes it easier to write it out. And what's happening is that everything is being written as a power of 10. It's very simple and very straightforward. This is why it's used. It's kind of like, if you ever noticed in your science classes, what system are they using? Not the English system, the metric system. Why? Because everything is based on 10. 10, it makes logical sense to people. Now, ironically enough, the British, for many years, the French invented the metric system in the early 1700s. And at the time, the British were constantly at war with France, so they refused to adopt it. Then the colonies broke away from England, and all of a sudden, somewhere along the way, England decided, oh, what the heck, let's use the metric system. And now we're the ones who are stuck with the English system. There's apparently very few people, very few countries who still use the English system. It's like the United States and a few tiny little island countries. Everybody else has got metric. But even in science class, like if you're in science class, everything is done with the metric system. There's no pounds, there's no feet. It's all kilometers and meters and grams. And also in baking. Does anyone here do any baking? No, not yet. Maybe when you graduate and you have your own house. Everything is done in metric in baking because the weighing is so important. If you're, well, you'll find this out one of these days when you try to make cupcakes for something. You'll look at the recipe and it'll say, put 100 grams of flour in the bowl. And you'll say, what's going on here? This is all metric. It's extra important with baking to get everything just right. And so they use the metric system. Well, now you know, so don't be shocked when you see that. When one day you're going to say, I'm going to make cupcakes. I know what I'm doing. Okay. And as long as you don't blow up your room, the cupcakes taste anything like cupcakes, you'll feel successful, but you'll also have gotten an education in the metric system. All right. Well, anyway, so scientific notation is based on that same logic. Now, in a couple of ways, we did get lucky, though. We may not have adopted the metric system, but early on, Thomas Jefferson proposed that we go to a decimal monetary system, which is why we have dollars and cents. A dollar means 100 cents. Because the British had a system at the time where each pound was worth 240 pence. Now, that was a bit awkward, you can imagine. So we did at least decimalize our money, but that's as far as we got. Um, so yes, that worked out okay, but everything else, yeah, we still have we still have miles and feet and inches and all the rest. There's some really truly bizarre measurements in the English system. Like in liquid measurements, there's actually a measure called a jigger, which is like an eighth of an ounce or something like that. It does exist. If you want to have some fun with this, go to Wikipedia and look at all these different measurements, official measurements in the English system, and there's all kinds of crazy sounding ones that represent different fractions of an ounce or a gallon, and they're out there and they're still valid words. A jigger. I don't remember the exact amount. I know, but you know what? Because it would be very awkward, Mick Jigger. No, we're going to look this up right now. Now that we're talking about this, how much is a jigger? Mick Jigger. I like that. Oh, look what these are glasses used by. By the way, you're not supposed to know about this if you're under 21. All right, here it is. It is 0.0117188 gallons. It's an ounce and a half. Okay. So pretend you never saw these shot glasses here. These are meant for making mixed drinks, and they'll have often one side will be an ounce, one will be a half an ounce, that kind of thing. So the word jigger is an actual. This is like a leftover from the English system, but it is a valid measure, an actual valid measure. Anyway, all right. So enough of that fun stuff. So we're going to start by noting that for any number, we can rewrite it as a power of 10, but the method we'll be using is we're going to make sure that the number we come up with is a single digit for the decimal point, and all the rest will follow afterwards. So this one can be rewritten as 1.22 times 10 to the 6th. And again, it's because we want to save space when we write. It's just easier. All right, let's see a few more examples. And of course, 10 to the 6th equals a million, so you should not be surprised to see this. This is 1,220,000, so we're going to multiply 1.22 times 10 to the 6th, and that will give us the result that we're looking for. All right. In other words, this is how you reverse it, so to speak. Anyway, so just a reminder, let's look at this table of powers of 10. And, you won't be surprised to see any of these. For example, 10 to the 6th power is a million. This is 1,000. Okay. Now, let's go on to the next group. How about 10 to the 9th? Who knows what that's equal to? What is that called? A billion. That's right. And how about this one? Blank. Any ideas?
Trillion?
It's a trillion. That's right. Now, you might think it stops there with the naming, but you know what? I found this very interesting Wikipedia page, and we're going to take a look at it right now, and you're going to be surprised by some of these names. Watch this. Okay, so 9 is a billion, 12 is a trillion, 15 zeros is a quadrillion. 18 is a quintillion. You see, it goes on and on and on. And if we keep going, watch what we're going to find. Google is 1.0 times 10 to the 100th power. In other words, 100 zeros after the 1. Does that remind you of something you've heard of? That's correct. And in fact, the company name is actually taken from this word. They changed the spelling to make sure that they could copyright it. And before you know it, their brand name is called Google. But they took it from the number of Google, which is 1.0 times 10 to the 100th power. Okay. No, Googleplex is, I think it's 10 to the Google power. Let's double check that. That's the next step up. That means 10 to the, 10 to the Google power, which means 10 to the 10 to the 100. Yeah. Or 1 followed by a Google zeros. That's a lot of zeros. Okay. But the word Google, the company that you know and love as Google, is based on, or the name is taken from one Google, 1.0 times 10 to the 100th power. I guess it sounded cool to those guys. And so that's where that name comes from. Wow. So a lot of the names that we know out there are coming from surprising sources. For example, our friend Starbucks is based on a literary reference. I'm going to tell, well, and whenever I ask this question, either people have heard this before or they haven't. You can't figure this out, but there's a character named Starbuck. He's a sailor in the novel Moby Dick, which you all may have had to read in high school. He's one of the sailors in the Pequod with the mad Captain Ahab. How do you like that? Okay, well, now you know. And now we know the origin of two names that you see on a daily basis: Google and Starbucks. What else could there be out there? I don't know. Now, I'm going to show you an interesting example. I may have shown this to you before of when we might be tempted to use scientific notation to replace an enormous number. So I have it right here. I don't remember if I showed this to you or not. I don't think I did. This is a $100 trillion bill printed in Zimbabwe about 12 years ago. Why would a country need a $100 trillion bill? Inflation, exactly. So at the time this was printed, $100 trillion was roughly enough to buy a loaf of bread. Wow, that's a lot of inflation. It was getting up into the stratospheric territories, but look at all those zeros. Don't you think it would be a little awkward? How many zeros is that? That's 14 zeros. So in a case like that, you might be tempted to write it out as 1.0 times 10 to the 14th. They didn't see it that way, as you can see. $100 trillion. Well, since then, I think they've gotten themselves back on their feet, and their inflation rate is more or less normal. But at the time, it was completely out of control. And I don't think we'll ever see this again, $100 trillion. By the way, if you're a collector, I took this off of an ad here. You can actually buy one of these for your collection if you really feel like, wow, this is as cool as it gets. But anyway, so let's look at some other cases. Yes, convert to dollars. That was probably worth about $1 at the time. But anyway, so let's look at some more cases of scientific notation. Now, you can see that in each case, whatever number I started out with is going to be converted into another number where there's a single digit for the decimal point, and then whatever comes after that comes afterwards. What you have to do is start with that and then figure out what power of 2 is needed to write that out properly. In other words, here, if I write it as 1.24, in order to turn that into 124, I need to now multiply it by 10 to the second, which is 100. All right, so in other words, this is the same thing as this. Now here, you can see this was 2,148. In order to convert it into scientific notation, I would need a higher exponent, which is 3. And remember, 10 cubed is 1,000. So that means this is 2,148. And then 10 to the fourth, remember, is 10,000. So therefore, this is the same as 3.2154 times 10 to the fourth. Okay. Now, with the small numbers, less than 1, we can use scientific notation, but now we're going to wind up with negative exponents, as you can imagine. So let's look at a chart to remind ourselves what these actually look like. So this one, for example, is 1 millionth. This is 1,000th. And now you can see this one, let's try the millionth. Now, the zeros that all precede the first non-zero decimal after this decimal point, these are referred to as leading zeros. Okay, all the zeros that come after the decimal point, but before the first non-zero digit, are called leading zeros. And if you notice, there's a pattern here. The number of leading zeros is 1 less than this exponent. So for example, with 10 to the minus 5th, there's 4 leading zeros. With 10 to the minus 4th, there's 3 leading zeros. 10 to the third, minus third rather, there's 2 leading zeros all the way up here. Here, there's no leading zeros. Okay. By the way, I almost forgot to mention this. Let's go back for a second. Let's say that you are working on these. Suppose you're asked to convert, let's say this one, into scientific notation. And you come up with this result and you say to yourself, you know what, I'm not sure if that's right. There's a quick and easy way of checking this out on your calculators. So 3.2154 times 10 to the fourth, you could actually do this very easily by just putting 3.2154 times, actually, let me get my calculator out for a second, just to make sure that this is working out the way I think it is. So yes, 3.2154 times, and then you would need to put in 10 x to the y 4 equals. And by doing that, you get the right answer. But there's an even quicker way of doing this that's built into your calculator. You could write 3.2154. Now, if you look in your keyboard, next to the 1, there's a button called EE. If you type EE, 3.2154, second E, sorry, just EE, now put 4 equals. Guess what? It's going to give you 32,154. So in other words, EE means 10 raised to some power. All right. So in other words, it'll save you a couple of steps if you use it. So if anytime you need a power of 10, you can use this EE button. And it saves you a few keystrokes. It's not that big of a deal, but it's good to know that it's there if you need it. What? Oh, you had a fire alarm? Oh, I did not know that. Oh, that's not good because I had no idea. Luckily, that's why we have the recording, but still, that's pretty annoying. Wow. 3 days in a row. That means something's wrong with it, probably. Way back. Is that the one that's called way back because it's way back out there in the middle of nowhere? I'm starting to forget. I've been so long. It's been so long since I've been on the campus. I'm starting to forget the names of all these buildings. Is that the one that's like really brand new near Fort Awesome, or is that a different one? Oh, wow. It's the brand new one. Oh, wow. Well, you know what that means. They're still testing this stuff out. That place has only been open for like 2 years, I think. Fort Awesome. That's been there a while. That one, I don't know if the others were. That one was that name was chosen by a contest. I don't know if that's true of the other ones. Yeah, I guess
Well, I know that Far Side is called the Far Side because it's far off to the side, I think.
ah,
Way back is called way back because it's way back quite literally. So
let's see. And isn't there a one dorm that's just called the old or the new or something like that?
yeah, there's also the old, yeah.
Yeah, that's different. Because the funny thing is, at a private school, the buildings tend to be named after wealthy alumni who gave them lots and lots of money. But this is a public school, and so there may not be any rich alumni giving them money. So instead, they pick interesting names. But how do they pick the names? Does anyone know how they came up with? I mean, did the school just say it's going to be way back now?
I don't know, but it seems like they just went, well, this one's to the far side, so we're
Yeah,
going to call it Far Side.
right,
And
right,
this
right.
one's really far back, so we're going to call it
Oh,
Way Back. And then they were like, great, put it on there.
no, because I know that Fort Awesome, they let the students pick that one. They literally said, "What do you think we should call this place?" And that's what they came up with. The school did not pick that name, that's for sure. Um, wow. So if they build what if they build a tall building? Will it be the big building or something? Um, wow. I don't know. You'd think that at a performing arts school there'd be a little more originality there, but maybe not. All right, the really tall building, yeah. The old, maybe it's the oldest dorm. I don't know. I'm starting to wonder. Like the old, what is there a new as well? I don't know. But the thing is, I often have to walk past a bunch of these buildings to get to Starbucks because I'm often in my office till late hours when I'm really in and on the built campus, and I see them all the time, and they don't actually say anywhere what their name is, do they? Is there any place in those buildings that has the name written on it? I don't think there is. Doesn't that seem a little strange? It's like, yeah, you're just sort of supposed to figure out this is Fort Awesome. It doesn't actually say that. Are there? Oh, I've never seen one. Tiny little signs, really? I guess it's too dark to see them. But huh? Are they at least nice dorms for dorm standards? I mean, you've got enough room. Yeah. but they're all relative. Most of them are pretty new. None of them are extremely old. I mean, the entire school has only been around since the 70s. Sometime in the early 70s, the state of New York suddenly realized, all these children of the baby boomers are coming of age pretty soon. Maybe we better do something about it. And within a fairly short time, they like at least half the SUNY system was built within that period of time, because they realized, uh-oh, we're going to run out of schools for everyone. And so Purchase was built in the very early 70s. Now, I've heard a lot of rumors about what it used to be. I've heard rumors that it used to be a jail, and I've heard rumors that it used to be an insane asylum. But they're rumors. Who knows what to believe? But I don't think any of it, I mean, there was something there already. They just bought it out and they just turned it into a school.
It was a farm.
Was it a farm?
Yes.
Oh, that makes the most sense. But then why?
That's why they have the old cemetery there.
Oh, I never noticed that. But why did people say it used to be a jail?
People like to start rumors like that.
People like
I know.
People tell each other stuff, and then people are like, "Wow, that's fascinating. I should tell all my friends."
Maybe that's what it is.
I don't know.
Although I must say, some of those buildings, like the Natural Sciences building, the layout is very bizarre. It makes you wonder what happened. I can't believe those buildings were meant to be like that from day one. They must have taken over existing buildings and converted them somehow. Like in my office, the ceiling has got to be at least 30 feet up in the air. It's really strange. It's just, and there's tiny little windows in the top. Like people could actually observe me if they wanted to while I'm sitting at my desk. But all right, anyway, enough of that fun stuff about the school, since none of us, are any of you actually taking in-person classes right now? No. Yes. Oh, wow. What are you studying? The people are saying yes. What are you studying? David, what do you say? What are you studying? Dance. Oh, all right. I can see that. Dance wouldn't work too well online, would it? Design and tech. Okay. Music. Okay. That makes sense. But I guess it's almost exclusively performing arts. Everybody else is at home, I believe. Yeah, that makes sense. Yeah. Okay. All right. That makes sense. Music, of course. Rehearsal. I get it. The rest of us were almost like pariahs. They're like, don't come here if you don't have to, that kind of thing. Yeah, like if I called them up and say, listen, I want to come and visit my office for a minute, they might actually say no. Oh, but don't you know how much we have to clean it and sterilize it and all this and that? Don't even think about it. So I don't. Here I am. All right. Anyway, so let's get some oh, here we go. We need some examples of the very tiny numbers. So you can see what's happening here. These are the ones with a lot of leading zeros, and the exponents have to be negative. So here's the way you can remind yourself how to move these things around. This must be correct, because watch what happens. If I shift this decimal point 2 places to the right, it becomes 2.4, and that's also my exponent. Okay. If I shift this 3 places to the right, I have 1.53, and the exponent is 3. You see that? I shift this one to the right 4 places. Wait a minute, 1, 2, 3, 4 places. I get a 9.8, and my exponent is 4. Well, so that's not that bad, but we have to get used to it. Now, by the way, I wanted to mention something very strange that you may have encountered if you've ever traveled abroad. A number like 1,000, we know it's written like this, but guess what? That's not true in every single country. There are several countries where it would be written like this. Oh my God. Now I can tell you from experience that 2 of them are, or 3 of them are Germany, Brazil, and there's probably more in Portugal. Now, Germany and Brazil, I only know because people told me that. And one of them actually showed me his calculator that he purchased in Brazil. And sure enough, these two are backwards from what we do. I found this out in Portugal in a Starbucks. Yeah. I bought a €3 coffee, and on the cash register, it looks like this. Well, we know what this means. What does that mean?
Isn't that like a euro?
That's right. That's a symbol for the euros. But, if you look at it and you say, wait a minute, why is there that comma there? Oh, that's right. I'm in Portugal. Of course. They have this other reverse system that we do. And I have no idea how this could have ever happened. You would think we all had the same standards, but we don't. There's still a lot of things that are not completely universal. And that happens to be one of them. Yeah. So if you know somebody who's from South America, take a peek at their calculator and you might see this. Yeah. That's how you'll know. Oh, I see you're from Brazil. And they'll say, how did you know that? Because look at your calculator. I can tell. You'll feel like Sherlock Holmes after that one. Like, how did you know? It's so elementary. Your calculator has the periods and the commas reversed. Oh, who would not notice that? But yeah, I thought you'd find that interesting. It just popped into my mind. Yes, it's absolutely true. And in fact, if you've ever traveled abroad and you tried to use a computer in another country, the keyboards are not identical in every single country either. The letters are not necessarily laid out in the same way. Or certainly the symbols are not necessarily laid out. They could be very different. Okay, so be aware of that. If you're going to sit down in front of a British keyboard, keep your eyes open, because you never know what's going to pop out of those keys. And in fact, somebody showed me a keyboard from Denmark. And the reason why it has to be different is because they have these special symbols that we don't have. This kind of thing. And so where do they put them? Well, they've got to make a decision. And before you know it, it's very different than an American keyboard. Okay, well, now, operations. It stands to reason that we may need to multiply or divide numbers that are written in scientific notation. Well, the process is very simple because it's based on the commutative property. And so let's take a look at some quick examples. How about this one? We got two numbers written in scientific notation. And now I want to keep it in scientific notation. What should I do? I'm going to multiply the constants together, or I should say coefficients. And then I'm going to multiply that by, and if you recall, watch this. From earlier in the course, we looked at the so-called product rule. Oh, that's right. So if I combine 10 to the third power times 10 squared, I'm going to get 2.8 times 10 to the fifth because I'm adding these together. Oh, there you go. Well, of course. What else? How else could it be? That's right. And if you're not sure now, your calculator, I'm not sure how it would react to this. I'm going to hold on one second. I'm going to see how it reacts. I'm going to put 2.0 E3 times 1.4 E2. Now it comes up with the actual number 280,000. Some calculators can turn this back into scientific notation. I don't think this is one of them. Oh, that's right. Unless you want to drop $100 on a high-end scientific calculator just for this purpose, I don't think so. So yes, this is all you have to do. And again, yeah, this is just what we just did. Now here's another one. I'm going to multiply these together to come up with 4.5. And when I combine these exponents, I'm going to end up with 10 to the second power, which is also, of course, equal to 450. Well, now I do want to show you another example that you might encounter where there's an extra complication involved. Let's put it that way. So let's try this one. 7.0 times 10 cubed is multiplied by 4.0 times 10 to the sixth. Now, when you multiply these two together, you're going to get 28, and then you're going to get 10 to the ninth power. There's just one problem. Remember, by convention, we want this first number to be one digit before the decimal and the rest come after. So what I'm going to do now is rewrite this as 2.8 times 10 to the 10th. The first one is not wrong, but the second one is the preferred method. One digit before the decimal. And the rest come after. That isn't happening here, is it? No. So a real purist would say, no, no, no. You want to switch it to this, but remember to adjust the exponent because these are now the same number, 280 billion. No, sorry, 28 billion. Yeah. $28 billion. Let me just double check that. 2.8 EE10. Yes, 28 billion. All right, I just wanted to mention that you could run into this case, and it could go the other way too. You might end up with something like this. If you started with this, then you would have to convert it to 2.8 times 10 to the 8th, okay, because this is less than 1. Same thing. You want to make sure there's one digit before and after the decimal, and then you adjust the power of 10 to whatever it needs to be. Okay, now division, as you can probably guess, is going to happen in a very similar way. I'll just divide the two coefficients, and I'll divide the, now remember here we're applying the so-called quotient rule, which we had a little earlier. Did those show up on my screen, those little ads? Oh, they don't. I just got this little pop-up ad for President's Day sales. And you didn't see that? Oh, okay. I was wondering. I was like, wait a minute. Because they're very annoying because, I didn't ask them to do that. And there it is. Oh, you did see it. Oh, okay. Maybe it went by too fast. That's right. I dispensed with it very quickly. I mean, they're just little ads and all. I know, but still. And occasionally it's useful. Like if it comes back and says, oh my God, we're going to get a foot of snow tomorrow. But anyway, so. Yeah, there's a way to turn them off if it gets too annoying. But the other day, you know what? I was on the chat room with Verizon. I was asking them about one of my products that I ordered, and the thing kept popping up. You know how it is with chat rooms. You never know when they're going to say something to you, and you don't want to sit there staring at it for too much time. So they're helpful in the sense that they'll let you know when there's a response from a chat room of some kind, and that's kind of nice. All right, but anyway, here's the quotient rule, which you'll recall from just last week sometime. I think we started doing this. A to the m over n is a to the m minus n. So that's what's happening here. The exponent here will be 7 minus 5, which means we have 4.1 times 10 squared, or you can just simply rewrite it as 410. All right, it means the same thing. All right. So are we ready for another one? Yes, we are. Now here's another nice one. The ratio of these two numbers is very simply 1.3. And here applying the quotient rule, we have 5 in the numerator, 8 in the denominator. So that new exponent is 5 minus 8, which is of course just negative 3. And that in turn equals 0.0013. Okay, now that was all that we need to say about scientific notation. What's coming up next is a little different. You might remember we watched a video where we're introduced to the Fibonacci sequence. Now, how cool was that? On the coolness scale, all right, you know what that means. All right, here we go. Are we ready? It's been too long since our last poll. We have to have polls every so often. Ooh, we got some big voters here, but beyond belief. Oh no, we've got some 1 through 3s. How is this possible? Oh, I'm so disillusioned. I should have compared it to the $100 trillion note from Zimbabwe. That one was really cool. I think you'll all agree. Well, you know what? We got some big ones and some little, well, only 2 people don't seem to care for it. All right, that's okay. Just wondering. Anyway, but what we're about to introduce here is a simpler type of sequence. There are many different kinds of sequences. The Fibonacci sequence is actually fairly complicated compared to what we're about to look at. We're going to introduce what are called arithmetic and geometric sequences. And what separates one type of sequence from another is the pattern that we establish. Okay, so now here you can see in front of yourselves, this is a sequence. And I think the pattern is pretty obvious. What do you think is coming next? And if I bet you $100, yes. 7, oh my God, yes. So in other words, you can see for yourselves that there's a pattern here. We don't need to write out every single element, which, by the way, these individual numbers are often called terms. And in general, we're going to write them out in the following way. The first term, we'll call it A1, A2, A3, all the way up to whatever we have. The A means it's a term. The subscript tells me which one it is. Okay, we're going to need that for the formulas that we're about to derive. Now, there's 2 types, as you can see, arithmetic and geometric. We're just going to touch on this today. So what is it that makes a sequence arithmetic? Well, what happens here is that there's a constant difference between the terms. So this one is arithmetic because each term is obtained by adding 1 to the previous term. And I think you'll agree that that means they have a common difference. The common difference then is 1. And therefore, this qualifies as an arithmetic sequence. Oh yeah, we don't want to forget the dots. This goes all the way up to positive infinity. Now, I'm going to show you some more examples, although one of them we've already seen, unfortunately. So this one clearly is arithmetic. Common difference is clearly 1. Now, in the second one, if you notice, the first term doesn't have to be 1. It can be anything. But here, you notice I'm not adding 1 to each term. What am I doing instead? We're adding a 3. So therefore, this one qualifies as an arithmetic sequence with a common difference of 3. Now, in the third case, again, we're not starting with 1. But look what's happening. The numbers are going down. Oh no, is that allowed? Yes, it is, because the common difference is just -1. And so, by the way, that means that this one is going up to negative infinity, down to negative infinity, rather than positive infinity. No, we're using a D in this book, D for difference. The N is going to refer to the term itself. Okay, so in other words, AN will be the nth term. As we'll see when we start looking at the formulas, D will be the common difference. Every book is different. You may have seen it with a different notation in a different book. Okay, and we'll see that. We're going to have examples. We're going to have formulas. Now, why would you need a formula here? What if I wanted to know, let's say I asked this question, what is the 100th term in this sequence? Well, you've got two options. You can write them all out, but that's going to take a long time. Don't you agree? The other option is to use a formula, which we will be defining next. But sadly enough, since this is where I stopped with my other class, I think we'll have to sadly stop it here with us. I know it's disappointing when this class is over. All right, I can hear the disappointment through the computer screen. And but you know what, we got plenty done today. Now, I do want to remind you though that next time we meet, I would like to do the second chapter 5 problem set before we get back into this material. And the second one is somewhat longer than the first one, so it might take up most of the class. But when we're done with that, we'll get back to this good stuff, and then the following Monday, we should be able to do the third one. And then that means we'll be completely done with chapter 5. And as far as the first test goes, that requires us to finish both chapters 5 and 6, do all the problem sets, and then do all the reviewing. So I'm thinking in terms of maybe early March before we really have to worry about it. Because already, I mean, it seems hard to believe, but already we have less than 2 weeks left in February. Okay, so anyway, so why don't we stop right here? And when you go home, make sure you tell everybody about that little quirky thing with the commas and periods, or else tell everybody about the $100 trillion Zimbabwean bill, or to see if they know the origin of the name Google. Don't you worry, you'll be impressing everybody with your knowledge of math trivia. Isn't that kind of what you're aiming for? When you hang out with people, aren't you trying to see who knows the most about math? Does that ever happen? You start getting into a contest like that to see who knows the most about math trivia? I bet you do. Anyway,
Not yet.
no, okay, but save these little tidbits for the right occasion. When
Oh,
there's
definitely.
somebody bragging about something in your room, and you're like, listen, do you know what the name Google actually means? And you'll put them in their place. All right. So I guess I'll just see you all on Thursday. All right. Bye.
Take care, Professor.
Okay.
Bye,
I
thank
can
you.
never
Thank
find.
you.
See you in economics.
Bye. I'll see you then. Yes.